The invention of switched-mode power supplies became one of the most revolutionary pieces of technology developed in the 20th century. From this, full-bridge topology became a standard for high-power charging. However, its design presents significant challenges and complications within the relatively new electric vehicle industry. Our patented SDC technology simplifies charging for all stakeholders and has made some revolutionary changes. These changes emerge as soon as the AC waveform travels from a power station and reaches our infrastructure. We split the three AC phases into separate converters. Power moves through our novel flyback charging hardware as a squared sinus waveform. In one single stage, it performs power factor correction, rectification, galvanic isolation, and current regulation at over 300,000 times a second. Once rectified, the three SDC waveforms are merged on the output, producing high-quality DC power, which combines all safety and functionality in one step. The combination of our squared sinus waveform and novel flyback topology creates a powerful and unmatched duo. SDC's current control is localized and independent of the electric vehicle battery voltage, enabling more straightforward and precise control systems. The combination of a novel flyback topology means our charging units can stack together, creating a multi-layered parallel redundancy system. It uses fewer stages, features less complexity, and lowers lifetime costs. So why are we changing the way electric vehicles are charged? EV charging systems use full bridge, a voltage source transformer design which requires multiple stages of power conversion to turn AC to DC for charging. When the three-phase AC waveform reaches a full bridge charger, it is rectified, chopping the waveform from AC to non-isolated DC. The non-isolated DC then passes through a power factor correction stage. Its purpose is to reduce any reactive loads that energy companies charge customers money for, and to also meet international regulations. Throughout this stage, high-voltage aluminium electrolytic capacitors are deployed to store and smooth the ripple of the chopped current. A 1000-volt cable is then dug underground to transfer the non-isolated DC to the user console, containing yet another power conversion stage and costing the operator a significant percentage of the overall install. At this point, the DC is not galvanically isolated from the grid. Energy companies and district network operators require significant oversight and paperwork to reduce the possibility that their assets will not be affected if anything went wrong with the charging infrastructure, for example, if lightning strikes. Finally, the power reaches the last stage of conversion when the cable enters the user console, containing a substantial, isolated DC to DC converter, filtering and control feedback electronics. This stage is essential for isolation and voltage stepping between vehicle battery packs. Then, and only then, can the vehicle be allowed to charge using this approach. However, there is additional complexity, as the output regulation of a voltage source full bridge charger is dependent on the voltage feedback from the vehicle. Because of this, voltage source control is infinitely more complicated to design and program than the SDC technology, preventing a truly modular system using hundreds of full bridge chargers. Comparing the two approaches, the full bridge waveform's journey is overcomplicated, using a power supply design that is not suited for the environment and economics of electric vehicle charging. This conclusion is why we have spent the last 7 years combining our squared sinus waveform and novel flyback technology to create the SDC platform. We are here to revolutionize the future technology of electric vehicle charging. We make charging easier.